Welcome to this explainer. Today, we're going to take on a giant. We're going to tame the invisible, relentless beast that is electricity by understanding how it flows and, more importantly, the vital devices that keep us safe. Whether you're a pro technician or just someone wanting to understand the hidden forces behind your walls, electricity is an incredibly powerful tool. But it's also a potential hazard that demands absolute respect. Here's our roadmap for today. We've got 1. The flow of electricity. 2. Controlling flow with switches. 3. Fuses and circuit breakers. 4. Catching leaks with GFCIs. And finally, 5. Ultimate safety with lockout-tagout. Let's get right into it. Section 1. The flow of electricity, or as I like to call it, the relentless path. To tame it, we have to establish exactly what electricity fundamentally wants to do. You see, electricity is essentially this dynamic, continuous movement of electrons, and it absolutely requires a closed path to flow and actually do work. We call this a closed circuit. Think of voltage as the electrical pressure pushing those electrons along, and current as the actual flow rate. For a circuit to be usable and safe, it needs 3 things: a source of power, a load that converts that electrical energy into work or heat like a motor or a light bulb, and a complete conductive path, usually made of low-resistance materials like copper wire. If that path is broken, the flow instantly stops. But if the path is complete, well, that current will flow relentlessly. Now, since electricity flows so relentlessly, we obviously need a way to dictate that flow. So, moving on to Section 2, controlling flow with switches, commanding the current. When you put a switch in series with a load, it acts just like a gatekeeper. It's completely binary. It interrupts the path to stop the current when it's open, and it completes the path when it's closed. In the electrical and HVAC worlds, we classify switches by their normal, unactuated state. Normally open, or NO, means the contacts are apart and the circuit is broken until you physically or automatically actuate the switch. Normally closed, or NC, means the path is complete in its resting state, and actuating it stops the flow. Whether we're talking about a simple wall toggle, a thermostat, or a massive contactor, they all rely on this exact same fundamental principle to command the current. But what happens when that current gets a bit out of hand, becoming excessive and hazardous? That brings us to Section 3, fuses and circuit breakers, protecting the system. These guys, fuses and circuit breakers, they're basically your system's frontline defenders. Their whole job is to open the circuit before the wires can overheat, burn, or just fail violently. Now, a fuse is a one-time overcurrent device. When the current exceeds its rating, a tiny metal element inside physically melts, permanently breaking the circuit. A circuit breaker, on the other hand, is a resettable overcurrent device. When it detects an overload or a short circuit, an internal mechanism trips, throwing the handle to a middle position and opening the contacts. Both do the exact same vital job, protecting your conductors and equipment from destructive overcurrent. And this leads us to the absolute golden rule of electrical maintenance. Always correct the cause, never upsize a breaker to stop tripping. I know it can be incredibly tempting to just throw in a bigger fuse or upsize the breaker so it stops nuisance tripping all the time. But if you do that, you've just completely removed your safety net. A larger breaker could allow your wiring to carry way more current than it can handle, causing it to overheat and potentially catch fire. A blown fuse or a tripped breaker is a symptom, it's not the root cause. You absolutely have to correct the overload, the short or the failing motor before you restore power. Now, while fuses and breakers do a great job protecting your equipment from heat, they won't necessarily protect you. A standard breaker might not trip if a tiny, deadly amount of current leaks through a human body to the ground. That takes us to Section 4, catching leaks with GFCIs, protecting the human. The ground fault circuit interrupter, or GFCI for short, operates on a very simple yet incredibly crucial rule. What goes out must come back. Here's how this builds into a life-saving mechanism. A GFCI is constantly comparing the current leaving on the outgoing hot conductor with the current returning on the neutral conductor. In a perfectly healthy circuit, those two numbers should be exactly the same, right? But if they differ even a little, it means electricity is escaping on an unintended path. And if you're in a wet environment or working with damaged wire insulation, that unintended path could very well be through a human being to the ground. And get this, the GFCI is so incredibly sensitive, it can detect an imbalance of just 5 milliamps. To put that into perspective, a standard circuit breaker might not even trip until it hits 15 or 20 amps. That's literally thousands of times higher. When a GFCI detects that tiny 5 milliamp difference, it breaks the circuit in a fraction of a second. We're talking around 1/40th of a second. This drastically reduces the severity of a shock, preventing the current from fatally disrupting the heart. GFCIs don't replace breakers, and they for sure don't replace safe work practices, but they are a vital layer of defense specifically designed to protect the human body. As amazing as those automatic protectors are, we really can't rely on them when we're intentionally exposing wires to perform maintenance. When professionals open electrical panels, they rely on absolute manual isolation. That brings us to our final section, Section 5, Ultimate Safety, Lockout Tagout, Absolute Isolation. This is lockout/tagout, often referred to as LOTO. It's the ultimate procedure where an authorized worker uses personal locks to physically prevent anyone from restoring power while they work on a system. It ensures that the equipment remains completely de-energized. The lock provides the physical restraint, ensuring a switch or breaker cannot be moved, while the tag identifies exactly who applied the lock and warns everyone else not to touch it. Every authorized worker on a job applies their own personal lock, meaning the machine cannot be turned back on until every single worker is finished and safe. This requires a strictly structured, non-negotiable process. First, you shut down the machine normally using its standard controls. Second, you isolate the energy by opening the correct disconnect or breaker. Third, you apply your personal lock and tag to that disconnect. And fourth, and honestly this is probably the most critical step of the whole thing, you must verify that the energy is actually gone. You try to turn the machine on to ensure it doesn't start, and then you use a properly rated meter to test the conductors. Here is the absolute crucial point. A disconnect or breaker position is not proof of zero energy. Test before touch. Off doesn't necessarily mean dead. You might look at a disconnect handle, see it in the off position, but you literally cannot trust your life to a piece of plastic. Internal contacts inside a switch can weld themselves closed due to heat or wear, leaving the circuit fully energized even when the handle says it's off. Plus, if you open a main service panel, the parts ahead of that main disconnect are still fed directly by the utility and remain live. That's why the golden rule is always test before touch. Assume every wire is fully energized until your own meter proves otherwise. To confidently verify zero energy, pros use what's called the live-dead-live method. It's a three-step dance. Step 1, you prove your meter is actually working by testing it on a known live source. Step 2, you test the target circuit you are about to work on. This is where you expect to see 0 volts. But wait, you don't stop there. Step 3, you go back and test that known live source one more time. This proves that your zero reading actually means the circuit is safe, and not just that your meter leads broke or a fuse blew inside your tester during the second step. It's the only way to be absolutely certain you're about to touch a live wire. So, I'll leave you with this final thought for today's explainer. Is the electrical system around you a tamed tool or an unpredictable hazard waiting for a single mistake? By understanding how current flows, how switches command it, how breakers and GFCIs stand guard, and how rigorous procedures like lockout/tagout provide absolute isolation, we can safely harness this incredible energy. The next time you flip a switch, reset a tripped breaker, or see a maintenance lock on a panel, remember the incredible forces at play and the rigorous safeguards required to keep us all safe. Thanks for joining me, and stay curious.